Today we're going to look at a different type of number known as a complex number. And this will come back into your world in our next unit when we start looking at quadratic. So you might recall from Algebra 1 when you studied sets of numbers, natural numbers, whole numbers, integers, rational numbers, and irrational numbers, and those are all amongst the set of real numbers. It turns out that there's also some other numbers that are outside the set of real numbers. And to think about that, you've got your naturals, your wholes, your integers, your rationals, all within that set of reals, and then irrationals, also part of the reals. But if you remember from Algebra 1, occasionally you would be asked to take a square root of a value, and the value was negative. And so we know that we can't take a square root of a negative number, at least in the set of reals. So that equation, x squared equals -1, we didn't have a solution for it. So somewhere along the line, somebody recognized that we still needed to be able to operate even when we had square roots of negatives. And so they came up with this concept of an imaginary number. And we used the letter I to stand for the square root of -1. And we can use that to simplify any square root of a negative. Find complex numbers. These are numbers written in standard form, a plus bi, a and b both real numbers. The number a is the real part of the complex number, and then b times I is the imaginary part. So all the real numbers are complex numbers with no imaginary part. All the imaginary numbers always have an imaginary part. And numbers that are pure imaginary have no real part. So thinking a little bit about being able to operate with complex numbers, we can actually add, subtract, multiply, and divide them. When we add complex numbers, we're going to first write these in standard form, a plus bi, and then we're going to group together the real terms and the imaginary terms, much like grouping together like terms when we're dealing with variables. 2 plus 2i plus the number 1 minus I, we would write that as 3 plus 1, which is the real part, and 2 minus 1 times I, that's the imaginary parts, and then simplify and write that in standard form, 4 plus I. To subtract, very similar approach. We're going to group together the real and the imaginary terms, keeping in mind that we need to distribute through that negative sign. So 6 minus 2i minus complex number 1 minus 2i would give us 6 minus 1 plus -2 plus 2 times I. So 5 plus 0i, and that would be equal to 5. So let's go ahead and do some practice. Go ahead and pause the video. You can come back and put your answer. So let's go ahead and take a look at some of your work. So number 1 and number 2 are both addition problems. It should be relatively straightforward to group together the real number parts and the imaginary number parts. So number 1, you should have 5 plus I, and number 3, 5 plus 3i. Number 2 looks like 4 minus 2 plus 6 minus 3i. You can see that we distributed this negative sign, so -2 and then minus 3i. So 2 plus 3i is your simplified standard form. And then number 4, 3 plus 3i. So it turns out that we can also multiply complex numbers, much the same as we learned how to multiply polynomials by using the distributive property repeatedly. So let's take a look at a couple of examples. So 2i times the complex number -1 plus 3i. So 2i times -1, that's -2i. 2i times 3i, 2 times 3 is 6. I times I is I squared. Now let's take a look at something here. This is pretty important. If I equals the square root of -1, then I squared equals the root of -1 squared, which just equals -1. So this is -2i plus 6 times negative 1, negative 2i minus 6. Similarly, we can go ahead and do the distributive property multiple times. 6 times 4, that's 24. 6 times negative 3i, negative 18i. 3i times 4, that's plus 12i. And then positive 3i, negative 3i, that's negative 9i squared. Well, remember, I squared is negative 1. So let's work on combining it. 24 minus 18i plus 12i minus 9 times negative 1. So now I have 24 minus 18i plus 9. So that's 33 minus 6i. And there's a couple on there for you to practice as well. So take a moment to check your work on the practice problem. 6i plus 3, or in standard form, 3 plus 6i, and number 2, 4 plus 3i. So just as we can multiply complex numbers in similar ways to the way that we multiply polynomials, we can actually divide complex numbers in much the way that we divided polynomials, in particular dividing polynomials that contain radicals. Remember, I is a square root. It's the square root of negative 1. And so in order to rewrite these division of complex numbers as a complex number in standard form, we're going to multiply numerator and denominator by the conjugate. So given the example, 3 plus 2i divided by 1 minus 2i. We're looking in the denominator, 1 minus 2i, and recall the conjugate has the same terms, but opposite signs. So 1 minus 2i and 1 plus 2i. So we multiply those out, and remembering that I squared is equal to negative 1. In the numerator, we get 3 plus 8i plus 4 times negative 1. The denominator is 1 plus 4. So you look at the simplified version of this, negative 1 plus 8i over 5. I no longer have an I, which remember is a radical, in the denominator. So go ahead and take just a moment to practice one on your own, and we will check the answer. So together, let's check our work. So 5 minus 4i, we're going to use 5 plus 4i as a conjugate, and multiply the numerator and denominator times that conjugate. So using the distributor property twice, 15 plus 12i plus 20i plus 16i squared, that's the numerator. 25 plus 20i minus 20i minus 16i squared is the denominator. When we simplify this down, 15 minus 16 plus 32i, that's negative 1 plus 32i. The denominator, we're no longer going to have a radical part, no longer an I. 25 plus 16, that gives us 41. So you'll want to be sure to take a moment and summarize your learning today. 2 things you learned today, 2 things you want to know more about, and 1 big question you still have. Be sure to bring those questions with you to class tomorrow, and we'll start off by taking a look at those.